Welcome to Wireless Future. I'm Emil Björnsson, and on the other side of this line we have Eric Larsson. How are you?
Good, Emil. How are you today?
I'm great. So it's raining outside here. Hopefully you don't hear it since I'm indoors, but you can always sometimes be afraid that all kinds of sounds were picked up when we make an audio recording like this.
Indeed.
So today I was thinking that we're going to talk a bit about analog. So there is so much focus on digital communications and digital computation and things like that. And I heard people talk about that, there are certain use cases for analog computations, analog computers again. But in this episode, I was thinking that we will take the communication side of that and talk a little bit about analog modulation and some related aspect with over-the-air aggregation. So, why are people going back to analog modulation? What is your take on that?
Yeah, that's a good question. I mean, I guess the first question is, are people going back to analog modulation?
Sure.
I think the answer at large is no. I mean, the mainstream techniques are digital, right? And that's the development we've been seeing over the many decades. So in a way, it's like when we discuss analog, why do you discuss analog? I mean, that was like, I don't know, pre-Shannon, right? Or maybe could even give like an anachronistic bit of a feeling. But there are applications and use cases and situations where analog modulation indeed does have some advantages, even say in the modern world. And I guess that's what we'd be focusing on a little bit today.
Yeah. So I also have this feeling sometimes that, when we are rapidly digitizing everything, then we sort of do it just because we think that it's always the best case, but then there will probably arise certain use cases where the analog methods have their benefits if we understand them.
Yeah, indeed. And I mean, even some old traditional analog modulation techniques are pretty good, right? Like analog FM for broadcast, for example, for radio broadcast, for example. But
I'm still using it in the car.
We do indeed. I mean, right. So where do we start this off, Emil? I mean, I guess maybe one question is really why analog at all? Why this bit of a revival that I think is fair to see that we have seen over the last few years? I mean, at least for selected use cases and applications, right?
Exactly.
And I think I would argue that number one is simplicity. I mean, you could take, you have a sample and you want to transmit it. Okay, so you take the sample and you send it as an amplitude, right? And that's it.
Yeah.
Now, is this good or not? I mean, simple or not? I mean, the question is still, is it good, right? And one obvious consideration, I think, is latency. I mean, if you just have like a single sample, you want to get it across, you don't have time for complicated source coding or converting into bits and all that associated processing and so forth. But it's also that there are applications emerging where maybe we don't need like all of the modern source and channel coding with performance guarantees that they come with and so forth. I mean, in inference applications like in sensor networks where you collect data or in machine learning applications where you might have vast amounts of data indeed and you want to aggregate, I mean, all this data over the ether, right? So these devices transmit the data and perhaps, I mean, the traditional performance criteria like block error rate and so forth and bit error rate aren't as relevant anymore, but rather other things like how fast does this learning model converge and so forth. And then it turns out that, just analog transmission of the data isn't in many cases such a bad option. And I think finally a point to be made is that there's actually an optimality aspect here. I mean, there are cases where linear analog modulation is optimum, right? If you just have a single channel use, a single dimension, so you send a single sample across, like over the Gaussian channels. I want to send you a real number X over the channel with Gaussian noise, then analog modulation is the best you can do. I mean, of course, if there's some kind of bandwidth compression or expansion involved, so that I'll send you this sample over multiple channel uses, or that's a different story. But for for a single channel used on linear analog is in some situations actually the best one can do.
Yeah, so I guess the usual selling point of digital modulation when you are teaching this is sort of one that you can, if you have a lot of data, you can compress it somehow, both the source encoding and then you add your channel encoding, so you can sort of have some kind of integrity of the received data. But you're saying that in situation where we don't need this kind of two aspects, that there would be more efficient ways of communicating.
There can certainly be situations where it's simply more efficient. Yeah.
Okay, but what if we are not then really bandwidth limited? We could transmit multiple times. Should we? And then I guess you would use a repetition code in digital communications. If you have a message that is analog, do you repeat it twice in that case?
Yeah, it's a good question. I mean, to start with, I think in digital communications, you wouldn't use a repetition code, right? You'd send your message and then you would encode it again using a different channel code, which is the same thing as to say just add additional like parity bits and then you send those across and combine the information actually from these, well, extra parity bits. For analog, I mean, going back to what I said, if you have a single sample that you want to send over a single channel used, then just send it, your value, x, okay, over the channel. So you map your x onto your amplitude and that's it. But if you want to add like some sort of error protection through bandwidth expansion, so you have a single sample x that you want to send over, let's say, 2 channel uses, so you have a 2-dimensional channel or 2 degrees of freedom, then you need a mapping from x to a 2-dimensional coordinate. And such mappings exist and can be optimized. They typically look like spirals that start in the origin. So then to apply the mapping, what you do is you look at the spiral and then you take your number x that you want to transmit, and then you travel a distance from the origin along the spiral. And whatever 2-dimensional coordinate that you reach will give you the 2 values that you should send over your 2 channel uses or over your 2 degrees of freedom. And conversely to like air quotes decode, then you should take your received 2-dimensional point, and you should check which is the closest point on the spiral, and then you should measure the distance along the spiral to the origin, and that will give you your estimate, say x hat, right? So that's like the way to perform bandwidth expansion using analog modulation. One can also do compression using similar techniques, but maybe leads too far here. So
yes. So when you're talking here about the degrees of freedom, is this like you have extra time compared to the length of the thing you want to transmit, or is it frequency, or how does it work here?
When I say degree of freedom, I just mean samples, right? And samples could be samples in the time domain or in the frequency domain. I mean, quite general, it's like you have some time frequency space that in which some waveform lives, right? And we know the number of samples you need to kind of like approximately describe or parameterize this waveform is the b times t, the bandwidth multiplied with its time duration. So when I say dimension or degree of freedom, it's the same thing as think of it as a sample in some discrete time representation, which is typically, I mean, through the sampling theorem, right? In comms applications.
Yeah, and this sort of discrete time representation, is this still useful when we work in analog, or I thought that was closely related to the digitalization of the signals?
Yeah, but you can always describe, I mean, a waveform that lives in some certain time frequency space by using samples, or rather, I mean, through an expansion in basis functions, and then much of in comms, then we like to use the sync basis, which is the sampling theorem. So in principle, certainly yes. I mean, you can always discretize because of the sampling theorem, more or less.
Yeah, exactly. So the sampling theorem is underneath there, and the only difference between
I mean,
I guess the only difference between analog and digital there is sort of that what are the samples that you're getting in analog is sort of given by the original signal, in the digital is sort of determined by your source and channel coding.
Yeah, you could think of it that way. You could also think like, I mean, digital modulation is a very advanced form of nonlinear analog modulation, right? Where you have some very complicated nonlinear mapping from your analog numbers to what actually goes out on the channels. When we speak of like, well, a little bit like a non-linear analog, yeah, okay, simple spiral mapping, that's one thing, but at some point it becomes so complicated that, you know, where do we draw the line? When does this become like digital or something else, right?
Yes. So when people are now starting to talk about analog modulations again, then it often comes together with this concept of over-the-air aggregation, where some kind of analog signal is supposed to add up over the air. So how does that work?
Yeah, so this concept of over-the-air aggregations, the idea here is to have that we have multiple transmitters that could be like sensors in a sensor network, or they could be like clients in the machine learning application or something. But anyways, like devices that have data to send, and we're interested in the sum of their data. And now let's talk about, like, to start with, at least aggregating a single sample. So then the idea is that they would just transmit using linear analog modulation this sample, and the samples would add up in the air or in the ether by virtue of the superposition principle of the wireless multiple access channel. I mean, in principle, this is like the superposition principle of the wave equation, right? I mean, we have multiple transmitters, multiple sources of electromagnetic waves, and whatever we receive here is going to be the superposition. So that's the idea of this over-the-air aggregation, which then naturally, I mean, requires analog modulation so that the signals add up. I mean, we need linearity in the modulation because we have linearity in the superposition itself.
Yeah. So as you were saying, there seem to be a number of possible use cases there where you sort of are maybe measuring the same or different things and want to aggregate that. It's a bit like telling people to how many are agreeing upon something, and then they raise their hands, and then you're sending different signals there. So suppose there are like two users that measure some things, or you will like to add them up, maybe just to get the sum or to get their average, which is just the sum divided by the number of things. What is required then if these two users should send their signals and make them add up nicely to the sum?
I mean, so what's needed here is that now, if we have an aggregator or like a base station or a receiver somewhere, right? So it's an antenna here, and then we have, like, let's say, two devices that transmit simultaneously some analog linearly modulated value. Then for these two values to add up the way we desire at the receiving antenna, then number one, we need to compensate for the difference in path gains or path losses. So these path gains have to be known at the devices, and they have to scale the transmitted signal with the like reciprocal path gain or path loss. Yeah.
Do they need to know each other's path gains, or?
Yeah, I mean, in the end, there'll always be, of course, a power constraint, right? And they will have to set some coordination is required to set the power so that, I mean, whoever is farthest away should use maximum permissible power, and the others will have to scale back in power. So some coordination is required in order to set that scaling factor. But that's, well, it's obviously a thing that has to be considered, right? But I think actually more important consideration is that they also need to rotate the phase to compensate for the phase rotation incurred by the channel, and that entails indeed two things. Number one is that these devices need channel state information that could be acquired through pilot signaling in the various forms. And number two, they have to be phase aligned. Just like in distributed MIMO, I mean, if you do joint coherent beamforming, the panels need to estimate the channels, but they also have to be phase aligned, right? I mean, it's like we got two devices here, and or you and me transmit to someone, and we know that someone, we know how far away it is. Okay, so we can compensate for a propagation delay, but we still need to agree on a time base so that we transmit at so we agree when is time zero. So that's also required there. So two things, I mean, channel estimates and this phase alignment or calibration among the devices. for this combination to actually add up, or for the signals to actually add up constructively at the aggregator or at the the receiving antenna.
Exactly, and this is where one needs to sort of to either, as you were saying, when we work in really the analog time, that it is the time delays or phase shift that we need to sort of compensate for, and when people are working with complex baseband models, we need to remember that there is not only an amplitude, there is also a complex phase and the complex numbers that we need to to deal with,
and that makes a great deal of a difference. I mean, when that's not, this phase is there, and it's very often the deal breaker in making these things work.
You can transmit with the same amplitude 1, but then one gets +1, another gets -1, and then your summation.
If your phase reference is off by pi, then we'll combine destructively rather than constructively, right? And then the thing won't work. So it is a bit like in beamforming from distributed or a MIMO array or distributed arrays, where you need them to be calibrated in such a way that the joint coherent beamforming works on downlink, right?
Yeah, so exactly. So that, but what I was starting to think about, that the concept of transmitting with known phase references from multiple places, sort of what you use in beamforming usually, but we talked about that in previous episodes. Do we create beams or do we create something else? But I guess the important thing is that at a desired location, the signals are adding up in this constructive manner. But then I guess normally when we talk about beamform, we sort of transmit the same piece of data from multiple antennas, and we make sure they add up constructively at the desired point. So the new thing here is that it can be different data that we're transmitting?
Yeah, certainly. I mean, and that's the whole point, right? I mean, that typically the aggregator or the receiving antenna here wants to learn the sum or the average or whatever. But let's say the sum, because sum and average are the same thing, more or less, right? So the sum of the data samples or values that these two agents are sitting on. And I mean, that's all again motivated by applications like where you want to learn, maybe infer the average of something like an average sensor reading or number, or in machine learning applications. Federated learning is one important use case where you have, in principle, I mean, you have like a machine learning model that lives in a cloud somewhere, and then you have clients that cooperate in training this learning model, and each client has its own training data, but the clients don't want to share the training data. They only want to share like updates to the model. So the cloud or the server broadcasts the model, the clients perform some local updates on it, and then transmit the gradient update. And these gradients updates should just be summed up or added up at the server. And it's exactly this summing up operation that can then be done through over-the-air aggregation naturally, right? Because then, I mean, all that entails is an arithmetic. It's a sum over the values per component in the gradient vector or the model parameter vector that the agents want to convey. So I think that might be one of the more compelling use cases for over-the-air aggregation, indeed, because the sum operation comes naturally in there in terms of like adding up these gradient updates.
Yeah, and I guess there's also things in like the general detection kind of theory that maybe that is also partially the same thing here, where you add up an arithmetic mean of measurements, and then you make an hypothesis test to decide is it above or below a threshold, for example.
Absolutely. I mean, so these data values that the devices send could be, I mean, log likelihood ratios, for example, right? And then they probably should be added up at the fusion center to make an optimum decision and so forth. So that's another maybe actually simpler example, which is, I mean, just as compelling, I think, or rather, I mean, in that case, the question is also, I mean, what are the amounts of data here? Because in sensor networks, if these are just the occasional decisions, then the dimension of the data is very low, right? But in this machine learning application, it's like there could be model parameter vectors that have thousands or many thousands of components, and then suddenly efficient use of radio resources becomes a bigger deal on a different scale. So potential benefits then through this sort of analog aggregation technique could be larger.
Yes, so we can clearly find a lot of use cases when we would like to add up different things, like you call the arithmetic mean, for example. But then there's also the whole world of other kinds of mathematical operations. I mean, the first thing that comes to mind is the geometric mean, where you sort of want like to multiply different things together. Can that be done over there as well?
Yeah, it can. I mean, there's actually a large class of functions that can be computed through over-the-air aggregation, and the trick is to pre-process the data samples through some appropriate nonlinear mapping, and then transmit, let them aggregate, and the aggregation always happens through addition, because this is by virtue of the superposition principle of the wave equation. And then after the superposition has happened, you take the received sample and you apply other, like air quotes, inverse nonlinear mapping, right? So, for example, if you want to compute the product of the data values rather than the sum, then what you should do is to take each value, and the client first takes the logarithm of the value, and then transmits the logarithms, and then the logarithms add up, and the receiver takes these logarithms that added up and computes the exponential. And then we know that the exponential of log of a plus log of b is equal to a times b, right? So product is easy, and many other functions can also be like computed. The class of functions that can be computed this way is called nomographic functions, and this is like a field in mathematics that study properties of such functions and so forth. But maybe the sum and the product are the most obvious examples that.
Yeah, and I guess eventually, if you have something that is very non-linear from the beginning, where you need to apply this kind of like exponential functions and stuff, or logarithms, I guess dynamic range could be one.
Oh yeah, it'll certainly be an issue. Sensitivity to noise. I mean, it's it's absolutely. There's a host of non-trivial questions associated with the use of such mappings and aggregation this way.
So. Let's try to make this mapping now to analog modulation. So normally when I think about analog modulation, like I'm listening to radio in the car, then you just take your audio signal and you put it out there and transmit it directly. Here, if I understand it correctly, it's still like you are deciding on your own like pulse function. Like could be a sync or something else, and then on top of that one you multiply the exact measurement number, which is an analog number. So that is how you generate it.
Yeah, when we say linear analog modulation, I mean there's always a waveform underneath, of course, but we think of it like take some predefined waveform and just multiply its amplitude and rotate its phase, right? Which in the complex baseband formalism is just multiplication with a complex scalar, and then you send whatever the result over your channel.
So when analyzing this, do you need to go back and start in analog time, or can you use these complex baseband models?
No, you can work in with a complex baseband model. I mean, of course, that entails some assumptions on, for example, that there is no dispersion, but it can be done. I mean, you can always eliminate dispersion by applying an FFT and a cyclic prefix, which is effectively OFDM modulation. And I mean, so in principle, the short answer is yes. You can think of this like sample by sample complex baseband.
Yeah, that's great because we are so much more used to working with the complex space. I mean, to some extent, a lot of the textbooks are about we start in analog, then we rewrite everything until we arrive at the digital cases, and then we stick there. But then every time we change something fundamentally, we sort of need to start over. But yeah, it's good that we can work in the digital again. So it seems like one of the really important thing here is that we can phase shift things correctly so that they are aggregating coherently. So what if we don't have channel state information at the transmitters?
Yeah, so that's a challenge indeed. If you don't have channel state information at the transmitters, or they aren't phase aligned, so you can't rotate the phase to make your data points or samples add up constructively, then we have a bit of a problem because that's the whole point of this over-the-air aggregation. And in the literature you'll find some papers that claim to do non-coherent over-the-air aggregation and so forth. Well, to some extent this can be done, but it doesn't seem to be very competitive. And the fundamental problem here is actually rather easy to understand, I think. So, if you just have a single channel use available, and you're going to send like two values that are to add up, right, constructively, then if you aren't phase aligned or you don't have transmitter channel state information, then you might have bad luck, so that you're off in phase and the values don't add up, but rather they add up with a minus sign or something. So rather than computing x plus y, I compute x minus y, which is obviously not what I wanted, right? And kind of the only way of solving that is to use multiple degrees of freedom. So now suppose that we had now instead 2 channel uses, 2 degrees of freedom. Then, well, we could take each client here could take his data point, like x and y, right, for the 2 clients, and multiply it with any favorite orthogonal sequence of choice. I mean, it could be FSK, could be Hadamard sequence, could be anything, and then transmit it. And then we're good. Then we can, at the receiver, just project onto these orthogonal waveforms and recover x and y. But that effectively is equivalent to just taking turns and using the channel. So, okay, we got 2 channel uses, you send X and I'm silent, and then you send Y and you're silent, and so forth. So, in a way, it's like non-coherent over-the-air aggregation requires the expense of additional degrees of freedom, which could be like that we use more time symbol or samples, more samples in the frequency domain, or both, or more spatial. I mean, you could receive your signal with more antennas and hope that, well, at least at some of the antennas, the phases don't add up. I mean, at least at some of the antennas, the phases add up like reasonably well and so forth. But I mean, over-the-air, non-coherent over-the-air requires the expense of additional degrees of freedom, or essentially repetition in some form. And that's an important thing, I believe, to convey, actually, that again, I mean, you can find claims that have been made that over-the-air works with non-coherent and so forth. Be very careful. I mean, always trace this back to the foundations in comm theory and look at what is the actual dimension of the signal space and so forth and what's going on here. I think the one exception might be in applications where there is an abundance of degrees of freedom, like for example with visible light. We anyway communicate non-coherently, right? I mean, in the sense that I have a photo sensor here and I got 2 lamps and I turn one of them on, I turn the other on, and I turn both of them on. It's just like, well, the intensities are going to add up, and that's because the signals add up non-coherently. It's just because we have such abundant bandwidth. Everything is non-coherent anyway, and I mean, in such a setting, it could actually like work, but fundamentally, circumventing or not having this ability to phase rotate properly at the transmitters would require some form of repetition, which in a way just takes out all the benefit from the start, right? Because the whole point of this over-the-air aggregation is that, let's say we have k devices, then we have to aggregate the data simultaneously from, then ideally we would like save a factor of k degrees of freedom or radio resources, right? But now if we had to repeat the thing k times, the gain is gone. So it's just a horribly important thing to be able to pre-rotate the phase at the transmitter.
Yeah, so as you were saying, one of the possible benefits here is then that, if you have k users that should send their data, and the only thing you're going to use the data for is to aggregate them, then instead of encoding them separately and transmit them over there, decode them, and then add them up at the receiver, we could let them then add up over the air. So that was sort of, in a way, reduce the things by the data or the utilization of the channel by a factor k, then I've started to think about it. Isn't this also going back to sort of multiple access channels where k users could potentially transmit at the same time? You can get the multiplexing gain and decode the user data in that particular ways.
In a way, I mean, we of course have a multiple access channel, right? The unique aspect here is that we are interested only in the arithmetic sum of the values, and but certainly, again, I mean, to reiterate the point, I mean, or the whole selling argument for over-the-air aggregation is that we save on radio resources, because k devices can send their data samples simultaneously, and as opposed to like requiring k different radio resources, which could be time or frequency or space or something else, then they just send simultaneously, and so we'd save like k times ideally.
Yeah, exactly. And I mean, the weak spot in my example was that you would need to have k receive antennas in order for it to work out, to decode them at the same time. So then you need this k times.
Yeah, and then we're in the MIMO game, which is
exactly
a story in itself. So yes.
Yeah, and talking about MIMO now, I'm also thinking out loud. So if you have multiple antennas. If you don't know the phases at the transmitter side and you have multiple receive antennas, you will sort of get different linear combinations of them with these unknown phases. And I guess by solving a linear system of equation, you can sort of decouple the transmitter signal from the users, but you will still have an unknown phase, I guess. So you cannot get everything out of it.
And that's the difficulty to make this work really well for MIMO, because if you think of it, if you have an array of receiving antennas, then, well, for each one of the devices, there is not going to be a single phase rotation, which is optimal, let alone good for all of the antennas, right? With some luck, there might be a phase rotation that's good for but there's not going to be a phase rotation that's good for all the antennas. So, MIMO isn't, or put it this way, I mean, over-the-air aggregation becomes less and less useful when you have MIMO for that reason. And
yeah. So this whole thing reminds me a little bit about what we talked about with context-aware communications in episode 29, where you design your physical layer for the context, which in this case is to sort of add up data. So as you were saying, one of the key benefits will then be that if you're going to add up k different signals, then you just do it in one shot directly. So that's sort of much more efficient. Then if you look at what are the challenges or weak spots, I guess that the first thing, which is the traditional thing with analog communications, is sort of noise, that you get some kind of soft degradation of your signals by just adding noise, and you can't get rid of it. What are the other potential drawbacks with this?
Yeah, so I think one drawback we already touched upon, and that was the need to have accurate or at least good enough transmitter channel state information and phase alignment, right, to make the signals actually add up constructively, which is a non-trivial technical or engineering challenge indeed. I mean, it's something that's considered non-trivial for distributed MIMO, for example, to make the panels operate phase coherently, right? And now we're going to have like hundreds or even thousands of small wireless devices out on the field that's going to do all this in real time. So that's one thing that needs to be, that has to be in place. Another thing is that in my view, the most perhaps compelling application, namely training of machine learning models, then what the devices actually send are updates to gradient update vectors, right? And typically these gradient update vectors, they are compressed in some way. I mean, one of the standard methods for compressing them is to sparsify, to take a vector that's maybe 10,000 components long and look at which are the 100 largest components and set all the others to 0. And then you end up with a sparse vector, and that's then compressed in using some technique. Could be using digital techniques, could be compressed by applying random projections and then L1 norm or lasso type of reconstruction and so forth. And now for over-the-air aggregation to work here, then this the sparsity patterns have to be the same at all the agents, otherwise this won't work. I mean, and this compression, I mean, say for example that we compress by sparsifying and then applying random linear projections, then well, the sparsity patterns have to overlap, otherwise we'll have to use the same random projection compression at each one of the agents. And I mean, very often the sparsity patterns aren't the same, and then the gains quickly evaporate here. So I think that's like one major drawback, that I mean it all at the surface looks competitive when you think of like, oh, I got these vectors of dimension like with 10,000 components and we can send them simultaneously, they all add up in the air. But in reality it isn't like that. It's more like, well, I have this vector of 10,000 components and I have a small subset of the components that are actually non-zero. You have a vector of the same dimension, but you have a different subset of components that are actually non-zero. And then, you know, well, it's not enough to just transmit the non-zero components, right? We have to transmit the whole vector, because the sparsity patterns don't overlap, and then the gains are mostly gone. So that's a challenge. And
but I guess the counter of that challenge might be that one of the things that people learn in machine learning when you do updates is that it can be better to do many rough updates than a few really detailed ones. So if this allows us to sort of do more quick rough updates, then maybe
certainly.
we get the
gain. Certainly true, but still, I mean, you know, we in scenarios with heterogeneous data and so forth among these devices, then the sparsity patterns might not overlap at all, and then it's like you lose what you had gained. Other challenges, I think one is that, I mean, because the data are transmitted unprotected over the air interface, then it'll be like easier to eavesdrop, which could entail leakage of information about your training data that you don't want to reveal, for example, and it's potentially easier to spoof the links. Since there is no, like, I mean, in digital communications, usually we always have like an error correcting or error detection code that verifies the integrity of the data, right? Like a CRC check, and now we just send over analog. There is no such a thing naturally. So there are certainly a number of like drawbacks and challenges here. Some obvious, some maybe less obvious, and some more application dependent. I think the ones with the sparsity patterns and all that is quite application dependent to machine learning. But of course, this also means there are many like interesting research challenges, right, to undertake. So in the end, I mean, it's a fascinating, I think, let's say, technology and a fascinating prospect to save K times the radio resources.
Yeah, it really is a fascinating thing there, and I understand that people are like to analyze this as well, because it's sort of on the edge it might, or at the surface, I mean, it might look a bit like, oh, this is similar to sort of situation we know channel state information you transmit, use spacetime codes. But then if you use spacetime's code, then all the transmitters need to know all the data so they can shuffle them around in a predefined way. And here, the whole point is that every user have their own data. So it sort of becomes problems that resembles what people analyzed in the past, that with new twists that make them fundamentally different. So yeah, it's really excites researchers. So we touched upon MIMO, what would happen if you have multiple antennas, mainly from the perspective whether that could solve the lack of channel state information transmitted. But what if we have multiple antennas at the receiver side, for example, and you have these multiple users, they should phase shift things. Then if you phase shift the signals so they add up constructively on antenna 1, will they add up on antenna 2 as well?
No, not necessarily. I mean, again, this is the point I think we did touch upon earlier. I mean, but the short answer here is that we MIMO many of the gains of over-the-air transmission seem to or aggregation seem to evaporate indeed. But this is precisely the point, right? That there's no phase shift that's good for all the receiving antennas. So that if the devices adjust their or like invert the channel phase rotation for receiving antenna number 1, then receiving antenna number 1 is going to certainly receive the desired linear combination or sum of the data points and so forth. But at the second receiving antenna, I mean, the channel phases are all different, right? And it'll receive more or less like a random linear combination of the data points, which is typically less useful. So I think to properly, let's say, discuss over-the-air aggregation with MIMO, then we need to clarify very clearly here the fact that there are two kinds of channel state information that we might or might not have, right? I mean, one is channel state information at the devices, which includes also the ability to phase align and so forth. That's the first. And the second is channel state information at the actual receiving array, which is typically easier, but anyway, I mean, it has to be there in order to do like meaningful coherent processing. And if the devices have channel state information, certainly, I mean, you can like optimize phase rotations per device, which are in some kind of average or overall sense good. That certainly can be done, and then you can apply appropriate receiving, combining, and so forth at the array. And if the devices have multiple antennas, you can do more clever things, obviously. That requires like more channel state information in a way, because you'd have it for every combination of transmit, receive antenna, and so forth. Without channel state information at the devices, then, one can still just have them transmit and decode in a way like air quotes blindly, and that isn't in the end. I mean, that's also workable. So,
but there can be some ambiguity left there.
Yeah, I mean, so if you just think of it, if you just have like an antenna array, and then you have devices out there just transmitting blindly, you need some form of receiver channel state information to process the data, right? And then you could opt for either having the devices send a common pilot so that you effectively estimate the sum of the channel responses to these devices, or you could have them send orthogonal pilots so that you estimate the individual channel responses and so forth. So there's like a wealth of the design space is quite large. I think that's one thing here, yeah.
So if we take a brief look at sort of cutting-edge research, perhaps. So you have written a paper that you will present at the conference called SPORC 2022. I guess it's in July. It's called Optimal MIMO Combining for Blind Federated Edge Learning with Gradient Sparsification. I guess the name of it is actually a nice abstract of what you're considering. But if you should motivate someone to take a closer look at this paper, what is it that you're looking into here?
Yeah, so I mean, the paper deals exactly with this issue that I just mentioned, right? How to most effectively use a MIMO array receiver when we have devices that send data through over-the-air aggregation, and the driving question that motivated the paper is to look at whether the concept of over-the-air aggregation as originally envisioned is actually a technically sound way to go, or whether it is better to just apply more like conventional style spatial multiplexing techniques to separate the streams from these devices. And more specifically, we looked at the case where the devices don't have channel state information, so we have to rely on some sort of blind transmission, and then we compared a scheme that's been suggested in previous literature where devices or the agents used a shared pilot and the array just estimated then like the sum of the channel responses. We contrasted that with the case that the agents rather each has a unique orthogonal pilot so that we can estimate the channel responses individually. And then, of course, we can apply like zero forcing combining, right? Or any like linear estimate that we want. of each signal independently. And maybe no big surprise, I mean, the spatial multiplexing technique with orthogonal pilots turned out to be a lot better. And one of the main reasons for that is that it also allows the devices to use individually designed sparsification and compression schemes. So we don't suffer from this issue of requiring a common sparsity pattern that we talked briefly earlier about, right? But that the standard over-the-air aggregation actually demands. So the short story is that, well, if you got a MIMO array, then it's typically better to just have the devices, well, pick an orthogonal pilot, transmit their data, and then use spatial, like MIMO processing techniques to separate the streams. And, you know, that also allows you to use any sparsification and gradient compression scheme that you like. The exception, I think, and which is important to point out, though, is if you have more devices than you have antennas, then this is not going to work. So you can't do like, I mean, the zero force combining, for example, is undefined, right? Or if you have more devices than you have samples in your coherence block, so that you can't afford to give orthogonal pilots to everyone. But most probably, I mean, in the use cases that I could see at least, is like, well, we're probably going to have a lot of antennas. I mean, 5G, not to talk about 6G, will use massive MIMO, right, in various forms. So we have all these degrees of freedom. And unless you're at very high carrier frequencies and very high mobility, then you'll have enough samples so that you can afford orthogonal pilots to those that you want to transmit simultaneously. And then, of course, in a way that could be like, maybe argued to be resource inefficient. I mean, if you spend, you know, half of your samples on pilot signaling, but in the end, that might not be such a big deal if you anyway can multiplex, you know, hundreds of devices at the same time, right? I mean, we're back at like the arguments that I think we've been making many times about massive MIMO for multiplexing and so forth. So in a way, one could say that, I mean, is this over-the-air aggregation or not? Well, that's debatable maybe, right? I mean, and then the conclusion is really that the way to go maybe is not over-the-air aggregation in this case. It's actually more conventional spatial multiplexing using massive MIMO style of transmission. So.
Yes, and it reminds me of some things that we worked on in the past that has to do with multicasting, which is sort of like you're going to broadcast the same signal, but not totally blindly, but you know that here is the location of users to consider, and then we have the choice between actually encoding the data separately perhaps for the users and just send different beams to them, or we could sort of transmit just once in a way that is a little bit towards both of them, and there you can use over there computations of the channel estimates by letting the user sort of transmit the same pilot sequence at the same time, estimate the sum of their channel, and then if you do beamform, you automatically forms a beam pattern that is sort of a little bit good for everyone. And I suppose you are using sort of the similar kind of approach in your paper here.
In a way, it's like if you have a shared pilot, which is what, I mean, our conclusion was that no, don't use a shared pilot, give everyone orthogonal pilots, right? But
yeah, but there is the alternative in terms of channel estimation.
Yeah, certainly. I mean, in the literature, others have considered like the possibility of using a shared pilot, and in a way, it's like the dual kind of setup of multicasting with a shared pilot, right? So it's a nice point indeed. Yeah.
So I guess then we sort of, if we try to wrap up, what are then some of the use cases for over-the-air aggregation? Well, one is of course the whole thing with the distributed updates of machine learning algorithms where you want to aggregate things. Then we were just mentioning aggregation when in channel estimation, where you anyway want to estimate the sum of some people's communication channels.
I mean, that's a form of over-the-air, right?
Yeah, exactly. So are there some other good use cases that comes to your mind?
Yeah, I mean, anytime that we're interested in, or rather this way, I think we got to separate here on one hand, the use of analog or even linear analog modulation techniques, and on the other hand, over-the-air aggregation techniques, where we are interested in this arithmetic sum specifically, right? And I think for analog in general, there are certainly like other applications. One that's quite interesting, I think, is distributed principal component analysis, for example, where essentially, agents are sitting on data and they run like a local little PCA, which gives them a unitary matrix, and then rather than sending that through digital modulation, it could be sent just flat out over the channel using analog. And if you send over a MIMO channel, you get something like H times U, and then you can do all sort of fancy like MIMO techniques to recover the subspace and combine the subspaces and so forth. So certainly for analog, for over-the-air aggregation, I think we mostly covered. To me, it seems that the most compelling use case would be for this federated or distributed learning sort of applications, but then we have to be aware of the drawbacks, right? Which, to reiterate, are that number one, with MIMO processing, some of the gains just vanish, and we have this requirement on like common sparsity or compression and so forth, which can actually be quite limiting, and we have the sheer fact that if things happen over analog, then eavesdropping becomes easier and so forth. So, but it's certainly, an exciting. I think it's a very nice topic for research and development, certainly. And in a way, it's like
And even if you have access to the most sort of advanced MIMO arrays and things like that, in some cases in the future, there will always be situation where you might want to save on hardware costs by having a simple receiver that can and then aggregate.
And don't get me wrong with the MIMO, right? We talked at some length about MIMO when you don't have transmit channel state information at the devices, but if you do, that's a different game. And then I think the science isn't entirely settled there, like how large are the gains and when are there gains. One thing is that the design space is quite large, right? We have to play with channel state information. How accurate is it at the devices? How long is the channel coherence? How many antennas do we have? How many devices do we have? What does the propagation look like, by all means, and so forth also, right? But absolutely.
Yeah, so to wrap up then, it seems like it's fair to say that there are some specific situation where analog modulation and over-the-air aggregation will actually be particularly useful, and that there is worth to spend time analyzing this further in the future. Is that the correct assessment?
Yeah. Certainly, yes.
Great. So thank you very much for sharing your insights and views on this topic. And we meet again in the next episode.
Thank you, Emil. It's fun as always.
Thank you. Bye-bye.